In this second problem, I've asked the students to sketch the shear and moment diagram of the following beam. The beam is simply supported with two cantilevers. It has a point load of 3 kips at the end of the left cantilever, and then a uniform distributed load that goes from the left support all the way to the end of the right cantilever. The uniform load has an intensity of 1 kip per foot. The first step here is to determine the vertical reactions at the two supports. And we're going to do that by determining the equivalent resultant of this distributed load here, which is 1 times 12 plus 5, that's 17. And that load acts in the center of the 17-foot span that the load is distributed. Because it's uniform, it's in the center, and so that's 8.5 feet. By simply doing sum of moments about the left support, we find that the reaction B is equal to 3 times 5, the moment of this point load here, minus 17 times 8.5, divided by this distance here between supports, which is equal to 12. That gives us a reaction B of 10.79 kips. The reaction at A has to be 9.21 so that they add up to 20 kips, which is the total vertical load going down, right? So vertical equilibrium is restored. Okay, so let's now move our attention to determining the shear diagram. So first we see we have a point load here. We're going to move from left to right as it's usual. So 3 kips going down. And then that stays constant because there is nothing happening here in addition to the point load. So that's a constant shear. Then it goes back up because of the vertical reaction at A, which we already found is 9.21. So minus 3 plus 9.21 gives you 621. Then the shear goes down uniformly at a rate of 1 kip per foot for 12 feet. So that takes you to negative 579, right? So 621 minus 12 times 1 gives you minus 579. And at that point, due to the vertical reaction at B of 1079, it goes back up to 5. Minus 579 plus 1079 gives you positive 5. And at that point, it continues to go down at the same slope of 1 kip per foot for 5 feet. So 5 minus 5 closes at 0. So that all checks out. And the last thing we're going to determine is the point of zero shear. Because we know that when the shear is 0, the bending moment is maximum or minimum. In this case, it's a maximum. So since here we have a shear of 621 and we're going down at a rate of 1 kip per foot, this distance here has to be equal to 621 feet. Now let's move on to the moment diagram. So from the shear diagram, we can easily construct the moment diagram by realizing, right, shear is constant here, so the moment is going to be increasing at a rate of 3 per foot, and so 3 times 5 gives you negative 15, right? You can also see that here by just equilibrium. 3 times 5, 15. Negative 15. And so then let's move on to the other end. You'll see how easy this works. So from the right, we see that this moment here has to equal the area under the shear diagram, just in the same way that we obtained it here. But here it's a triangular area, so the variation of the moment is going to be parabolic. 3 is going to be 5 times 5 divided by 2. That's the area of this triangle. That gives you 25 divided by 2. It's 12.5, and that's negative. And then, because we have a uniform load, we know that this has to be a parabolic variation between these 2 points. And so we just connect these two with a parabola, and the last thing remaining is to determine the bending moment at the apex here. That can be found by adding to 15, negative 15, the area under this triangle here, which is 621 times 621 divided by 2. That's 19.28. So negative 15 plus 19.28 gives you positive 4.28. And there you have it. That's the way to sketch the shear and moment diagram of this simply supported beam with point loads and cantilevers and distributed loads. A fairly interesting problem that all students of structural analysis should be able to complete.